this is a potato and this is a chiku. And these two caused me one of the most embarrassing moments of my childhood. When I was 7, my mom sent me to buy potatoes, which already feels like a risky decision. Like, why are you trusting a 7-year-old with groceries? So I go to the store, I look around, and I find these things that are roughly potato shaped and potato colored. I bring them back home full of confidence and I put them on the table like I just completed a mission. My mom looks at the table and says these are chikoos. The worst part was I had to go back to the same shop to get it exchanged for potatoes. But if you think about it, the real problem wasn't that I was dumb. I just didn't know how to tell the difference. How do you actually classify these two? Same size, same color, same almost round objects. So what's the difference? Turns out it's just small things. Color, texture, and the way it feels. And over time, your brain starts realizing what's a chiku and what's a potato. You might be thinking this is obvious, painfully obvious, but to a toddler, this won't seem obvious at all. We need to understand how a human learns this and break it down to the simplest detail. Because once we've done that, we'll understand the fundamental principles of learning. And that's where we are headed. From how humans learned to how machines do the same thing. So now, imagine teaching this to a machine. You show it a lot of examples, and each example is something that is already seen before. When I look at a fruit, I notice things, or I call them features, such as texture, color, and how the surface actually looks. The machine can't see like I do. So all of these features get stored as numbers in something called a dataset. And along with that, we also give the answer or the label saying this is a potato or this is a chiku. The model learns from these examples. Just like linear regression, it combines these features into a single score. I've broken down linear regression in another video, which you can check out. In linear regression, what we were doing was taking each feature, multiplying it with a weight, and then summing it all up to get one value. That value itself was a prediction, like predicting a price or a continuous number. In linear regression, the score was the answer. But in this case, it's not. We are not trying to predict. We're trying to make a decision whether it's a chiku or a potato. So we take that score and convert it into a probability using something called a sigmoid function between 0, a potato, or 1, a chiku. Once we have the probability, based on a threshold, we will classify it as either a potato or a chiku. Same idea as before, just one small change where instead of a prediction, we make a decision. This supervised machine learning algorithm is called logistic regression. A model trained using this algorithm will look at an object and say that it's 60% sure that it's a potato. Now, if the threshold says greater than 0.5 probability means that this is a potato, then this object gets classified as a potato. But what if, just like me, it classifies a chiku as a potato? We need a way to measure not just if it's wrong, but how wrong it was from the actual class. If it says 90% chiku, but it turns out to be a potato, it has to be punished more than a 55% guess and then be corrected. That's exactly where log loss or binary cross entropy comes in. It tells us, on average, how wrong the model was. The model uses these errors to improve. Maybe the texture was a more important feature compared to color in order to classify this object as a chiku or a potato. Knowing this, it trains over and over again until it becomes a really good model. So now, when a new fruit comes in, the model will take a look at its features like texture and color, combines it into a score, and then converts it into a probability. So it might say, I'm 85% sure that this is a chiku. And based on a threshold, a decision is made. No confusion and no going back to the supermarket.